Let's talk about continental rifting. My name is Patrice Rey, and this talk presents some research that has been done in the context of the Basing Genesis Hub, an IRC Industrial Transformation Research Hub, and that's a research that carry on with a linkage project on Proterozoic basing. Continental rifting exists in a number of flavors. Wide rift mode of extension, when the deformation is distributed over many hundreds of kilometers. A nice example is in the Basin and Range in the southwest US. And if you carry on that extension, what you end up with is an oceanic basin, which is separated by continental margin, where we can observe hyper-extended continental crust. And that situation here is described on the right in the context of the South China Sea, where we can observe a very similar geomorphology when we compare the north and south margin of the South China Sea with the Basin and Range. At the other end of the spectrum, we know that sometimes rifting develop over a very narrow region, no more than a few tenths of kilometers. And the best example are, of course, the East African system and the extension that have produced the Lake Baikal in a very different tectonic settings. Continental collision for the extension in the Baikal region, and continental extension in the context of probably a very active mantle in the context of the East African rift system. We know from early days that there is a link between the width of continental rifting and the mechanical layering of the lithosphere. And we can say that, in fact, the spacing of normal fault says something about how many brittle ductile layers you have in your system. Typically, the spacing of normal fault here corresponds to the depth of brittle ductile transition. And if you have a lithosphere with one or two brittle layers or three brittle layers, you see that you have a combination of those wavelengths at the surface. In the 90s, the work of Roger Buck and Jean-Pierre Brun were extremely important in defining key concepts of continental rifting. In particular, they were both really active in the definition of narrow rift, wide rift, and metamorphic core complex. Typically, Jean-Pierre has done a lot of work using analog experiment to understand extension of multi-layered system. So when you have a system where you have two brittle layers, upper crust and upper mantle, you tend to develop narrow rift. If you have only one brittle layer above a viscous lower crust and viscous mantle, you tend to form a wide rift. And this is something that you expect, for instance, a mechanical configuration you expect when you are dealing with extension of orogenic domain where the crust has been thickened, and thermal relaxation has produced a high temperature geotherm. The metamorphic core complex mode only occur when you have some zone of anomaly in your system. So typically here, this is how Brun is able to simulate the formation of metamorphic core complex by the addition here of a low viscosity and low density anomaly here at the transition between the brittle and the ductile layer. And as you extend, this layer here form a nice dome. Very important also to understand the coupling between the brittle and ductile layer through various velocity of extension. So this is a study from Govers and Wortel in the mid-90s, and they show that if you extend at a velocity of 6 cm per year, for instance, what you tend to develop is a narrow rift. Deformation keep focalized in one zone. If you increase your velocity, then you increase the coupling between the brittle and the ductile layer, and you tend to develop a much wider rift system. Analog experiment again by Tyrrell et al. Again, Jean-Pierre Brun was involved in this one here. They show the development of wide rift and a wide rift with metamorphic core complex. Again, one layer of brittle layer here above ductile layer, wide rift mode, a nice domino distribution of normal fault, and you add a zone of viscosity and density anomaly, and you form a dome. We have now access to supercomputers through the NCI facilities, which means that we can test all these ideas in the context where the mechanical property of the lithosphere evolve during deformation, something that you cannot do via analog modeling. So here, for instance, one of the conclusions of these studies is that as long as the temperature at the MOHO is under 650 degrees, then you tend to develop one phase of narrow rift. Extension is localized at the beginning and stay localized, and you form a narrow rift. At the other end of the spectrum, what happens if the temperature is above 660 degrees? Then we are looking here at a situation that is typical of gravitational collapse of a thick and hot crust. This was presented. This is a graph was that have extracted from the paper of Roger Buck. It shows the temperature at the MOHO here, and in the abscissa we have the crustal thickness, and he maps the three different modes of continental extension here. The core complex mode in that corner here, thick continental crust and hot temperature at the MOHO. The wide rift in the middle here, and in normal crust or thinner crust and low temperature at the MOHO, the mode of narrow rift. But this graph, with that graph, you can ask the question: can we transition, from a core complex mode to wide rift to narrow rift? Clearly here, that image here suggests that we should be able to move back and forth from one mode of rift to another. So that's the idea we tested. In order to do that, we start with a model that sits somewhere over here, so a thick crust, 55 kilometers thick here, crust above the green mantle over there, and then we extend. And what we hope to do is to reduce the thickness of the crust and to drop the temperature as deformation unfold. And this, predict that we should move from core complex to wide rift to narrow rift. And in fact, this is what we observe. We have here very fast deformation of metamorphic complex. They always form first, and then you switch to a wide rift mode that evolve into a narrow rift mode. To understand that switch, in particular from the wide rift to the narrow rift, we need to look at the mechanical property through the stress field. So as long as you have a zone that decouple, a zone of weak crust that decouple the upper crust from the upper mantle, you are in wide rift mode. But once that layer disappears, you switch quickly to a narrow rift, and the narrow rift here start when the stronger upper crust and the stronger upper mantle are in contact with one another, and in fact form one single strong layer. So we know exactly what control that switch. To have a metamorphic complex mode, I think it is important to realize that what we need is to have a zone of weakness in the continental crust. This experiment here shows what happened when there is no zone of weakness in the crust. And in that case, you don't have the development of metamorphic complex. You go straight into wide rift and you remain there. So the experiment just show you sits here. So I have plotted here a number of situations. At T0, this is where we were. We started with a crust of 55, temperature 920. And then through time, the thickness and the temperature at the MOHO decreases. And of course, we move from core complex to wide rift and to narrow rift. So the conclusion of this is that, we know that we have a diverse rift systems in the world, and this is due to a diverse mechanical layering of the lithosphere. But what we have shown over the past few years is that the evolving mechanical property of the lithosphere during rifting also explain that diversity of rifting, because under steady state boundary conditions, you transition from one mode to another. So it is not like a continental rift developed according to one mode of deformation. It is completely doable for this rift system to evolve across a number of those modes. And that's it for me. Thank you.